So in this video, we're going to talk about curve sketching, and we use a lot of the information we've found when we're finding max and mins, relative extrema, absolute extrema, using our first and second derivative rules. So in summary, finding our critical values, we get those when f prime of x is equal to 0 or undefined. That's how we find our critical values. Our critical values are telling me a change in concavity. It can be called an inflection point, max and mins. So the first derivative test, if f prime of x is greater than 0, I know f of x is increasing. If f prime of x is less than 0, I know f of x is decreasing. If f prime of x changes sign, it tells me I either have a local min or a local max. If it goes from positive to negative, I have a max. If it goes from negative to positive, I have a min. Now, on this page, I don't know why I have some capital F's and some lowercase f's. These are all lowercase f's. We're dealing with all the same functions. Those are just typos. My second derivative test, if the second derivative is positive, it's concave up. If the second derivative is negative, it's concave down. If the second derivative at some value c is less than 0, we know c is a local max. If the second derivative at a given value c is greater than 0, c is a local min, provided that c is a critical value. And then if the second derivative, f double prime of x, changes sign, it's telling me I have an inflection point. That's where the concavity changes. So now our goal is to use that information to draw our curves. So the things we're going to remember when we're trying to make our sketches is find any intercepts we might have, determine if there's symmetry, it's an even or odd function, determine any asymptotes, find the first and second derivatives to know where it's increasing and decreasing, get our extremas, any points of inflection, find out where it's concave up and concave down. And once we know those things, we can kind of put the pieces together to make a graph. Okay, in this example, we want to sketch a graph given the information. So it says f of x is on the closed interval from -2 to 7. So my grid goes from -2 to 8. We're not going to quite use the whole thing. It tells me f of -2 is equal to f of 7, which is equal to -3. So these are giving me points to plot. So anytime they give me a point, I might as well plot it. So -2, -3. At 7, I'm also at -3. And then it says f of 4 equals 3. So at f of 4, I'm at +3. So I'm plotting the points they give me. Then it says the roots of f of x equals 0 occur at x equals 0 and x equals 6. So there's two more points I have at x equals 0 and x equals 6. So I've given all the points they've given me, I've plotted, and now they gave me this table showing me information about my first and second derivative. So for my first derivative, it said from -2 to 0, it's positive, so that tells me my graph is increasing if I have a positive slope. From 0 to 2, first derivative is still positive, so the graph is still increasing. From 2 to 4, it's positive again, so it's still increasing. And from 4 to 7, it's negative, so now my graph is decreasing. The other information I get there, because my first derivative changed from positive to negative, is at x equals 4, I have to have a maximum. Okay. Now I want to look at the second derivative. It said f double prime of x is negative from -2 to 0, so that tells me it's concave down. It's positive from 0 to 2, so that's concave up. From 2 to 4, it's negative, so it's switching and it's concave down again. And from 4 to 7, it's negative, so it remains concave down. So at x equals 0, we see that the slope is 0, first derivative is 0, second derivative is 0. At x equals 2, the first slope is positive, but f double prime of x is 0. So this tells me this is an inflection point. And I also know it's an inflection point because the concavity is changing. So when I look at this, what I like to do, just to help me see what's happening on my graph, I'm looking at the interval from -2 to 0. Then I'm looking from 0 to +2. I'm looking from 2 to +4. And then from 4 to the end to the 7. So I kind of have 4 regions here that I'm looking at to make my graph. So from -2 to 0, I know my slope is increasing, but it's concave down. So it's kind of like the bottom half of a parabola. At x equals 0, we know everything's 0. From 0 to 2, my slope is increasing, but now I'm concave up. So I've got to kind of have to switch this a little bit. And then from 2 to 4, the concavity changes to go concave down. And then these are all concave down. So in that little region, if I kind of blow it up a little bit more, it went from 0 to 2, from negative 2 to 0, from 0 to 2, and then 2 to 4, and then everything concave down. So right there was that inflection point that our concavity changed at. All right, let's try another one. It says sketch a graph of a continuous even function. So even means it's symmetric to the y-axis. It tells me that f of x has to equal f of negative x. It's closed over our interval of x values from negative 5 to 5, having a range of g of x values from negative 1 to 0. When x is greater than or equal to 0, my roots equal to 0 at every whole number, k, and the roots of g prime of x occur at k over 2. The first and second derivatives g of x exist everywhere except at x equals k, and g double prime of x is greater than 0 for all the x values not equal to k. Wow, that's a lot of information. So because they told me it's even, I'm only going to look from 0 to 5. And it told me my g of x values go from negative 1 to 0. So from negative 1 up to 0, I'm never going to go above it. And it said when x is greater than or equal to 0, my roots occur at every whole number. So that means I have a root at 1, 2, 3, 4, and 5. Now it told me that g prime of x is equal to 0 halfway between each of those. So I either have a max or a min in between each of those. Now it told me that g prime of x is equal to 0, or excuse me, is greater than 0, which means it is always concave up, except for x equals k. So if it's always concave up, where my zeros occur, they have to be minimums. So when I sketch this graph, it's going to go down, 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 down. My derivatives are 0 at my mins there, and these are all concave up. Because it's an even function, it looks exactly the same on the other side. So here's where we're using our knowledge of first derivatives and second derivatives to help us figure out what these graphs have to look like. Okay, for this one, we're actually going to do 4 different graphs. It says sketch the graph of a function f that is continuous on 0, 3, and has the given property. So the first one, from 0 to 3, it has an absolute max at 0, an absolute min at 3. So if I'm going 1, 2, 3 on my graph, the absolute max is at 0. My absolute minimum is at the 3. It tells me I have a local minimum at 1 and a local maximum at 2. So there are multiple ways I could do this graph, but this would be one, and that would be for that first graph. Okay, let's try another one. So let's try B. So I'm going to graph a new one. So we're graphing only out to 3. And it says this time I have an absolute maximum at x equals 1. I have an absolute minimum at x equals 2. So the other values can be anywhere in here as long as those are my max, right? The endpoints can't be higher or lower. Okay, so now we're going to graph C. So again, we're only going from 0 to 3. It says 2 is a critical number, but f has no local max or local min. Okay, so if there's no local max or local min, that means my derivative is never equal to 0. So if it's just a critical number, it means it's either undefined there or it's a critical point. So I could say my graph could look something like this. Right, concave up, concave down, but I don't have any local max or mins because my slope here, actually let me make that one go a little bit further, is never actually going to equal 0. And then our last one for part D, again, just going from 0 to 3. That's a terrible graph. Let me try that again. Wasn't very centered. So there's 1, 2, 3. There we go. It's a little bit better. I have an absolute minimum at 0, an absolute max at 2, local maxes at 1 and 2. Now, if I have an absolute max at 2 and a local max at 2, that's telling me it's the same thing, and then a local minimum at 1.5. So my absolute minimum at 0 means 0, I've got to be way low. At 2, I have to be way high. I also have a local max at 1, so it's got to be lower than the absolute max, and I have a local minimum at 1.5. So then I can kind of graph this through and know my graph has to look something like this. So it's important to pay attention to the given information to see how we can make those graphs look.